Yeah, so the recording's going. So hey, we're gonna jump back into this organic chemistry. And yesterday, or on the part one of the mini lessons for this, we did the whole front page of it. And I'm presenting over here. So we've got this all rock and roll. This is all done. We got the basic idea between carbohydrates and monosaccharides. And what we need to do now is figure out how we go from a monosaccharide, a monomer, to a polymer, or in this case, just a two-stepper. We're going to have to do the assembly process. And the assembly process is known as a dehydration synthesis, which sounds like a crazy big word phrase, but it's not as bad as it sounds. The opposite of a dehydration synthesis is a hydrolysis. And we're going to go ahead and highlight this together. Let me grab a highlighter. I feel like I'm a Khan Academy teacher when I do it like this. Just so you guys know, there are real people here. I'm not just talking to myself. Real people. Not animatronics. Okay. They're all they're going to answer all my questions. Perfect. So carbohydrates, dehydration synthesis, and hydrolysis. Carbohydrates, protein, and lipids are all synthesized and broken down by the same types of reactions. In dehydration synthesis, a hydrogen atom from one molecule joins the hydroxyl group from another molecule form water, leaving the molecules bonded to the same oxygen atom. For example, when two molecules of glucose are joined by dehydration synthesis, they form maltose and water, see below. In hydrolysis, complex organic molecules are broken down by the addition of components of water, hydrogen and hydroxide. Both dehydration synthesis and hydrolysis require certain conditions of pH, temperature, and the presence of particular enzymes. So let's highlight it. What was it? Dehydration synthesis. Okay, so we have three different types of macromolecule that are synthesized and broken down by these reactions. It's a list. What do we do with lists? We highlight lists. So carbohydrates, proteins, lipids are all synthesized and broken down. So synthesized means that they are built up by, they're created and broken down by the same types of reactions. So if you want to finish that highlight across and say synthesized and broken down by the same types of reactions, it's not a terrible thing because it is pretty much the topic sentence of what's going on here. I just like to separate out the list so that I can see that there are three different things there. In a dehydration synthesis, a hydrogen atom from one molecule joins with a hydroxyl group from another. So hydrogen, we know, just has an H. Let's grab a pen. That's just going to be my H. And a hydroxyl group, we have not yet figured out, but a hydroxyl group is an oxygen and a hydrogen bonded together. And if I happen to find those two things, and I can get them bonded together, I have HOH, which is another way of saying H2O or water. Or, huh. Yes, another way of saying, huh, or water. Yes. Okay. So in dehydration synthesis, a hydrogen atom from one molecule joins with a hydroxyl group from another to form water. So essentially, in a dehydration synthesis, we form water. So I'm just highlighting form water. It leaves behind the two molecules bonded to the same oxygen atom. Do we want to highlight that oxygen atom, or can we leave that off for right now? Let's leave it off for right now. We can always come back if we feel like we need to. For example, when two molecules of glucose are joined by a dehydration synthesis, they form maltose and water, see below. I am going to highlight the see below, and then I'm going to let myself know that I should definitely look below. I don't think that you would be surprised to look below at the big picture that's underneath of there, but just in case, perhaps. Now, for highlighting purposes, we would continue into hydrolysis. For educational purposes, I want to take a look at the picture because it's told me to look below. Make sense? All right, so for educational purposes, let's take a look here. I have two things that are really right there in front of me. I have a structural formula that progresses across here, and then I also have words that are just coming down here. So just so we are all on the same general page, then some of us are probably really going to enjoy the words. Agreed? I agree with you. So this right here is one of my glucoses. And then the other glucose is over here. So, and then you'll notice that I have highlighted, or it's been dotted out. Actually, I'll put it into highlight. I'm going to highlight it with a light blue. Right here, my HOH. which is our water. Leaving behind, if we then advance and look like, ooh, look over here, that's where that oxygen ends up. And that's where those two molecules. Oh, exactly. Yeah. Oh, the oxygen. Yeah, exactly. And there's the arrow that shows that we're looking at glucose plus glucose. Okay. If I do this, what I end up with is a maltose molecule. And water. And that's super duper messy on the screen. But in terms of actually isolating what we're looking at, hopefully that helps a little bit. Oh, no, it doesn't. No, sorry. Yeah, that's a bad squiggly. I over squiggled my squiggly. Let me under squiggle my squiggly. Correct. Yeah. You've made two monosaccharides into a disaccharide. Now, there is a way that you are going to remember this, which is probably going to be very helpful for now on and forever and to remember it. Let's see if we can make this work. So, when you are given, actually not bad, when you are given Crayola markers, what must you do with Crayola markers?
Put the lid back on the same marker.
You have to
put them together.
You have to put them together, right? Right? And you have to then build as long of a lightsaber sword as you possibly can. Agreed? Okay. So as long as we're all on the same page and childhood hasn't changed completely. But let's say that this is a monomer. And as a monomer, and this is a monomer, and let's call these two glucose. In the presence of the right temperature, pH, and enzymes, when these two get together, they go through a chemical process known as dehydration synthesis. And then what gets removed? Water. Now I've made a disaccharide. No. And if I had another glucose molecule and I had my disaccharide, I could connect them doing the process known as dehydration synthesis. And water comes out.
This will make us remember it more.
For sure. And then if I happen to take like a galactose, which is a monosaccharide, put it to these three other monosaccharides that have been joined, I would then do it by a process known as dehydration synthesis, and water comes out. So now I have a polysaccharide. Multiples. How long can polymers get? How many markers do I have?
Unlimited.
So if you're building large complex molecules, macromolecules like starch, polysaccharides, cellulose, a cell wall, tens of thousands upon millions of monomers, but yes.
So monomers are like the building blocks of polymers?
Literally. Not just like,
and then
literally.
Polymers are the building blocks of life? Right?
Sure. Yeah, I mean, that's what everything's composed of, yeah. Dehydration synthesis. Now, I want to take it apart. I got to put a little water back into it. Hydrolysis. And I've hydrolysized it, taking it apart. Put water back in, hydrolysize it. No funny voice that goes with that one. Put some water back in, hydrolysize it, and I'm back down to my monomers.
So water is valuable. If you put something in water, they'll naturally come apart.
They will dissolve those bonds. If it's the right temperature, pH, and enzymes are there. But if water is the thing that's holding it together, the HOH of water is holding it together, and then it bonds back to that oxygen, putting water back into it helps it to disassociate. And water, as a good solvent, takes care of it. I know, right? So if we go back now, and I'm gonna erase everything that I've just highlighted on here because it's pretty goopy. In hydrolysis, the complex organic molecules are broken down by the addition of the components of water, HOH. Both dehydration synthesis and hydrolysis require certain conditions of pH, temperature, and the presence of enzymes. So hydrolysis is breaking, molecules are broken down by water. Polysaccharides are made of monosaccharides, which are carbohydrates. Polysaccharides are also carbohydrates. Correct. The monosaccharides are glucose, galactose, and fructose. Correct. Yep, we're only talking about carbohydrates right now. You got it. So we do have a list here, so that dehydration synthesis and hydrolysis require conditions of pH, temperature, and particular enzymes. To make this work, it has to be in the right. You can't just toss them all together and think it's going to dissolve. If we go now to our questions. In the space below, show the hydrolysis of maltose. Would you like to draw it as a structural formula, or would you like to do it in words? You want to draw it? No one ever says that. Are you sure? You'd have to draw the entire structure backwards. Well, I know I can't do it with the pen on this tablet. It's not fine enough. So, you know what? I'm going to do it in words. You can do it in drawing. All right. So I'm going to do hydrolysis. So if I have a maltose and I want to hydrolysize it, what do I have to add? No. Part of the reaction. Yep. Correct. Yep.
Okay. When the two glucose come together, two OHs need to form a water molecule, and then that little oxygen that's left behind will like grab the two glucose and stick them together.
If you're doing a dehydration synthesis, yes. So if I take maltose though and I do a hydrolysis, what am I going to be left with? 2 glucose. I'm just going to go glucose plus glucose. Pancreas produces insulin, which controls your blood sugar levels, which is why when the pancreas doesn't work, we're talking about diabetes. What are the products of the hydrolysis of maltose? Well, you've just done it here. 2 glucose molecules, right? 2 glucose. And Benito, I'm just cutting those questions off because we're on the recording. So I don't want to get too distracting. Yeah, it's okay. So in what life process does hydrolysis occur? When would we find ourselves having to hydrolysize macromolecules? There you go. For sure.
Your stomach is adding water.
Correct.
And then the glucose that comes out is absorbed and then goes to your body.
Correct. So you eat a pretzel, a big doughy pretzel, right? Oh, delicious. A little bit of crusted salt on top of there, maybe dip it in mustard. I don't know what you do. But that's a complex carbohydrate. Your body doesn't process that and doesn't extract energy right away. It has to hydrolysize it first. What do we know that when you eat a whole bunch of pretzels, you have to do? You're drinking water. You know, when you eat part of it is just to lubricate the digestive system so that you're drinking it and it slides down right. But it begins that process. Now you have saliva, has digestive enzymes in it, starts to break this down. You have stomach acid, you have stomach solutions that have digestive enzymes, start to break it all down. This is when hydrolysis really starts to take off. All right. All right. Questions on a dehydration synthesis or on a hydrolysis?
Really complex materials made by water. Breaks it down so the body can use it.
Correct. That's what digestion does. All right, let's see if we can finish up disaccharides today and maybe even polysaccharides, and then we'll take a break from this, and that'll be a good recording length as well. So for highlighting purposes, we're talking about disaccharides. We really don't have much in here. Disaccharides are pretty straightforward. When two monosaccharides combine, they form a disaccharide. Okay, di prefix means two. A disaccharide can consist either of two molecules of the same simple sugar or two different simple sugars combined. Some common disaccharides are maltose, sucrose, and lactose. Well, I'm going to start at the end where I know I have a list. So I want to make sure that I know that I have the common disaccharides are maltose, sucrose, and lactose. And I'm looking at this second sentence. The disaccharides can consist either of two molecules of the same or two different. That's probably good. So we can get two molecules of the same simple sugar or two of different simple sugars. And I'm going to leave that pretty straightforward. That's a pretty basic highlight. There's only a couple of sentences. There's not much in there. If you end up having to reread that whole section to study for disaccharides, it ain't going to kill you. So it's all right. So the monosaccharides that make up the following disaccharides, and I think some of you have the photocopy where that's crossed out, right? And some of you don't. I don't know why there are multiple versions of it, but name the monosaccharides that make up the following disaccharide. So the maltose we know is what? 2 glucose, right? So glucose plus a glucose. Sorry, that's a bad G. And sucrose is a glucose plus a fructose. And lactose is a glucose plus a galactose. It is. Now I'm going to blow your mind. Lactose intolerant. Don't tell me if you are. We know what it does. If you're severely lactose intolerant, you cannot digest lactose found in dairy. So what that means is that when your body gets a piece of dairy in it, and let's say that instead of this being maltose, let's say that's lactose, what your body cannot do is dissolve that bond because you don't have the right enzyme. There is an enzyme additive, lactase, T-A-S-E, which allows you to break that down, and you take it before you eat ice cream or drink milk. Yes, if you're lactose intolerant, then you do not have that enzyme. Which means when you eat dairy, you have this big clunky molecule in your stomach that your stomach's like, no, why did you do that to me? Get rid of it if it's severe. If it's not so severe, you're like, oh, I drank a whole glass of milk for, oh dear, flatulence. Or someplace in between, you can have some diarrhea as well. So yeah, lactose intolerant crampy stomach, really upset, not comfortable because your body says, hey, you've got this big molecule. Let me break it down. Oh, I can't break it down. I guess you're going to be stuck with it. And let's get it through the system. And the system's like, wow, man, we could really use some of that energy, but we can't break that oxygen bond. That's it right there. That's the thing that your lactose intolerance doesn't allow you to do. That's it. Correct. Because when you drink a glass of milk, there are tens of billions of these molecules that exist in that glass of milk. So you're drinking it and it can't break any of them. That's right. The correct. Well, I mean, eventually it goes through your body as either comes back out if you're severely like, oh, I can't process it at all. If you are severely lactose intolerant, then none of it gets processed. But that's usually people who immediately throw it up as soon as they put it in their mouth. It's still liquid, but yeah. It's pretty rough. All right. So the empirical formula for maltose, sucrose, and lactose. And to do this, I need to do a little bit of molecular math. So, who's feeling pretty smart right now? Awesome, Zayden. Fantastic, brother. What is the empirical formula for a monosaccharide? He's looking. He's thinking about it. Yep. Sure did. That would be the simplest possible formula. I need the actual empirical formula. C6H12O6. That's correct. Great. That's one monosaccharide. Everybody agree? Great. I'm going to add it another monosaccharide. Everybody all right? Let's just add them together like they're variables, right? C12, H24, O12. Here's one problem with this. That's not right. What process? Say it properly, Benito. Dehydration synthesis. Oh, you're not? Oh, it's too extra. All right. I have to remove water, which means C12, H22, O11. Okay. Now, let me ask you a question. Are my hydrogens and my oxygens still in a 2-to-1 ratio? Hydrogen and oxygen. H22 to O11, is that 2-to-1? Sure is, because yesterday we learned that high carbohydrates stay in a 2-to-1 ratio, don't they? Hydrogen and oxygen, just as the same proportion of hydrogen and oxygen in the water. So when we go back to our packet and we look at this, what is the empirical formula for maltose? We know it is C12, H22, O11. And then you say, why is the empirical formula not double? Because what do we have to subtract? We had to subtract the water. That's good, right? If you want to add my little, here, I'm going to put this up here. If you want to add this in the margin, here, I'll zoom out a little bit more so you can see the whole thing. You want to put my little monosaccharide math on here. So this is a monosaccharide. This would be my disaccharide, my water, and then my formal disaccharide. So actually, this doesn't get a disaccharide moniker. Take that one off. For sure. Yep. It's good stuff, right? They wouldn't believe you. So if you went back in time to tell somebody about this, like back in the day, they wouldn't believe you. All right. So if you want to put that in the margin, that's a really nice little, there's some space off to the right of that, I think, to fill that in if you want to put that biochemical variable math. I will tell you that when you go to chemistry, that's not the way that we actually do it, but it works well for this experience. So how we can do our little variable math there. And then the last question on this, and I'm going to stop the recording. What are the common names for sucrose and lactose? So sucrose is just generally like table sugar. That's the stuff that you generally buy is sucrose. And then lactose is milk sugar. So fructose is found in fruits generally. Yeah.
Like a spike in energy because your body breaks it just has to break
one bond.
Oh, so the more bonds food has, the more time it takes for the body to release the energy.
That's correct. So the more bonds that food has, then the longer it takes to break it down, the more energy release is slow release. That's right. That's correct. So when you eat just a whole bunch of glucose or you eat a whole candy bar, you get jacked up real fast and then you crash. Christian. Okay, yeah. I'm gonna, do you want to finish polysaccharides? Do you want, or we can wait on that one? Okay, we can wait on that one. We can do it tomorrow. You know what? Yeah, we can wait on that one. I'll stop the recording, and then we'll finish that up tomorrow. Great.